please join me in welcoming Professor Chris Lintott.
Thank you. Thank you. Thank you very much. Thank you for being here. Thank you for joining online. I find at this time of year, as the nights start drawing in the Northern Hemisphere, we all need cheering up a bit. And I think given the state of the world, I thought it would be nice to do something uplifting. But instead of that, we're going to talk about the end of the universe. And I'll give away the punchline to begin with, which is that whenever astronomers have come to think about the far future of, well, pretty much anything, the news is pretty bleak. But we'll work through it together. So, let me give you the local version first. We know that our sun is a star. It's burning hydrogen into helium, and it's about halfway through its lifetime. The solar system and the sun formed perhaps 5 billion years ago, and in about 5 billion years' time, the sun will end that stage of its life. This is a timeline provided here by the European Southern Observatory that shows sun-like stars. We have younger ones that we've observed, 18 Scuti there, the sun at 5 billion years, and then the oldest solar twin star the same size and mass as the sun that we found is this star HIP 102152. It's about 9 billion years old, and so we haven't got to the point where sun-like stars have reached the next stage of their evolution. But when they do, the sun, having begun to exhaust the hydrogen at its core that it's burning to produce helium, will swell into a red giant star. And that thing on the right there is the sun to scale. And you'll read, if you go and look this up, you'll read one of two things. So this is about 5 billion years' time. You'll read that the sun will engulf the orbit of the Earth. So that's the first piece of bad news. Most news articles about this, or stories about this, have slightly terrifying artists' impressions like this one. This is obviously just before we're engulfed. But sometimes you read there's some hope, because you see the sun produces its light by converting hydrogen to helium, losing mass as it does so. About 4 million tons a second is lost from the sun's mass. And that means that the Earth is very slowly spiraling outwards. And so we are very slowly escaping this fate. It may well be, though people who simulate these things differ in their opinions, that by the time the sun swells into a red giant, we'll have just moved outwards. And we'll have a wonderful view of the incandescent surface of a star, except that we won't. Because I skipped over the other piece of bad news, which is that process by which the sun loses mass means that the balance between gravity pulling the sun together and the pressure of radiation which holds it up, generated by those reactions in the center, that balance is shifting slowly. And so the sun is heating up. It's getting hotter over time. Now, that's on a timescale that is mostly insignificant to our lives. It's definitely not what's causing global warming. The timescales we're talking about here are much larger. But in 1 billion years' time, the sun will be hot enough that the Earth will lose its atmosphere. And so what you really should be worried about is that in 1 billion years' time, we'll live on a rocky planet with no atmosphere. And so, even locally, the news is not good. But most of the lecture, I want to look further afield and think about the whole universe. And it is striking that when you look at the history of cosmology, the science of trying to understand the universe as a whole, of trying to predict its past, explain its present, and as we'll do tonight, look forward to the future. I said predict its past, understand its past, understand the present, and then look forward to the future. That while the beginning of the universe has attracted a huge amount of attention and lots of even quite theoretical work, thinking forwards, thinking about the far future, is a relatively niche subject. It's dismissed often. I really like, there's a famous book that was written, I think, in the late 70s, The First 3 Minutes by Steven Weinberg, which is still a brilliant guide to the basics of cosmology, to the start of the universe. But he dismisses the end of the universe in a few short paragraphs, and in fact says that the more the universe is comprehended, the more it seems pointless. I did say it wasn't going to be the uplifting lecture I hoped. And the marvelous Dyson, who writing about this stuff in the 70s, said that it's notable that even when astronomers do contemplate the far future, it's done in a sort of tone, a jocular and amused tone, as I've done this evening, rather than being treated as a serious subject. But I think as we go through tonight, you'll see that we can learn a lot about our universe by imagining its future. And by trying to understand and predict the future, we're able to test and think through all sorts of fundamental ideas. So I think it is an important subject. Now, there are some fundamental assumptions that we have to make if we're going to predict the far future of the universe. The first one, and the one that's probably most important, is that I'm going to assume that the laws of physics don't change over time. It may be that in the far distant future, gravity turns bouncy, whatever that means, or atoms start to repel each other, or a magic new force, which we might call the Lintott force, comes and influences things. But once you start doing that, you're basically writing fantasy novels or science fiction. So I think we have to assume that physics won't change. And we can, I think, justify that a bit because we think we've got evidence that the laws of physics haven't changed for the last 13.8 billion years, the time since the Big Bang. Evidence for that comes from some quite surprising places. This is the entrance to a mine in Gabon, a place called Okio, and this is a uranium mine here on the Earth. And about 2 billion years ago, it seems that what happened was that groundwater in the site got into the uranium, the ore that's down there, and the combination meant that this was able to act as a natural nuclear reactor. So for a period of time, the kind of nuclear reactions that these days we build great nuclear reactors to induce happened naturally. As far as we know, this is the only place where this happened. It's certainly the only place where we have evidence that this happened. And the reason we know that it happened was that we can see the products of these reactions are preserved in the ore that comes from the mine. And the ratio of those products, different types of strontium, for example, are the same as those produced in reactors today. And so what that means is that the fundamental constants which control the nuclear reactions can't have changed by more than a few percent over the last 2 billion years. Physics operated then as it does now. And we can play the same game cosmologically. People have used telescopes like this one. This is the Very Large Telescope, or half of the Very Large Telescope in Chile. There are actually 4 of these. And people have looked at distant spectra of active galaxies called quasars and looked at the details of the lines produced by elements in those galaxies. And again, the atomic physics matches what you can do in the lab today. So we know, though some people disagree, but the evidence seems to be that there's no major change in things like what's called the fine structure constant, or the speed of light, or the mass of the electron over the last few billion years. So I hope you'll allow me, for now, to assume that physics is going to be constant through the rest of time. Otherwise, this lecture stops here, which would be sad. Now, of course, I'm talking as if it makes sense to talk of a history of the universe. So that comes, of course, from the idea that the universe had a beginning. And that goes back to the early 20th century when we were beginning to understand how things moved within the universe. This is work that was originally led by Henrietta Swan-Leavitt at Harvard. She was employed not as a professional astronomer, but initially as an unpaid computer, somebody who worked on data taken particularly in the study of variable stars, stars that change their brightness. A task that I think even then was considered to be something of a backwater of astronomy. Nonetheless, observations had been taken with the college observatories telescopes, and they needed to be reduced and understood. And that was the task that Henrietta set herself. And she realized that amongst the many stars that had been studied, there were some which have a particular pattern in how their brightness changes. These are the Cepheids. This is a modern light curve which shows brightness over time. And what you can see here is that the star brightens and fades and brightens and fades and brightens and fades in a regular pattern. In this case, the gap between successive peaks and successive troughs is just over a month. It's about 31.4 days for this star. And you can make this measurement of period for any star that follows this pattern. Henrietta looked in particular at stars in this galaxy. This is the Small Magellanic Cloud. It's one of the satellite galaxies of the Milky Way, one of two large companions that we have. It's actually being consumed slowly by our own galaxy, which we'll talk more about later in the year. But for Henrietta's purpose, the key thing here is that it's far enough away that you can assume that all the stars in it are approximately the same distance. In the same way that if you wanted to know the distance to a friend's house in New York from London, you probably don't care where in New York they live for that measurement. And so all she was doing was she was measuring the brightness of these things and then the period. And she realized there was a relationship between the two. That's what the graph shows on the right. On the bottom axis, you've got the period. So the stars on the right here take longer to pulse. The ones on the left take less time. And on the y-axis, the higher up you are, the brighter you appear in the telescope. And why that's important, if I show you two sources of light, for example, if you know they're at the same distance, then you can use the observation you make of their brightness tells you something about their real brightness. You know that this torch is doing rather better than this one, I think, because you know they're at the same distance. So because Henrietta knew all these stars were at the same distance, and she now knew the apparent brightness, she knew their relative actual luminosities. She knew how bright they actually were. And this is a relationship between how bright the stars actually are and their period. And this is crucial because now anywhere in the universe where you see one of these stars and you can measure its pulsing, you can look at how bright it appears, but you also know how luminous it is. And thus you can calculate the distance. You'd know if this torch was 3 feet in front of your face or 3 miles away, because you have some sense of how bright it is, or I could give you the wattage. So this is a really crucial breakthrough in astronomy, because for the first time, we can measure the distance to things beyond the solar system with reliable measures. And in fact, it wasn't long after Henrietta died in 1921 that astronomers were able to calibrate this scale. So we got an absolute distance. This brings us to Edwin Hubble, who, using new telescopes, managed to spot these variable stars in distant galaxies. Most famously, this is the Andromeda Galaxy. This is his image of it, taken with a 100-inch telescope in California in 1923. And you can see at the top, there's this star mark that's marked VAR, not a football reference, but a variable worth checking. And this is, in fact, a Cepheid. And so Hubble was able to take these things, measure their distance, and thus the distance to these galaxies. And as discussed in previous lectures, he came up with these measurements. He came up with this relationship between the distance to a galaxy and how fast it's receding. Here's the modern Hubble Space Telescope version. So you have this rule that the further away a galaxy is, the faster it's receding from us. The further away a galaxy is, the faster it's receding. That gives you the idea that space itself is expanding. And once we run that backwards, then you get the idea of this Big Bang 13.8 billion years ago, just from this measurement that space itself is expanding. This was work from the middle of the 1920s, but there'd been theoretical work around the same time that helped astronomers understand this. Depending on your nationality, you credit some of these 4 gentlemen with the work. On the left, we've got Alexander Friedman, who is Russian, who did the first work towards what's now called the appropriate metric, which describes such an expanding universe in the mathematical language of Einstein's relativity. Friedman rather tragically died in 1925 after eating an unwashed pear while on his honeymoon, which I'm mostly telling you to cheer you up. Second is Georges Lemaitre, who's a Belgian, who was the first one to say that if there is this expansion, there might have been what he called a primeval atom, a beginning of things, a Big Bang. His cheerful story is that having been in the army in the First World War, he was denied promotion after he spotted out a mathematical error in a military manual and was told off for insubordination. Howard Robinson, next up, is an American cosmologist, sort of looks the part, I think. I know him, apart from his cosmology, because he chaired what was called the Robertson Panel in 1953, which declared that UFOs are not a threat. Which is helpful. And on the right is Arthur Walker, who is a British mathematician who ended up at the University of Liverpool, where he mostly his obituaries are interesting. They're half about this cosmology, and they're half about the fact he hated paperwork. So he's a man after my own heart. But these two, FILRW, cosmology's greatest boy band, together get credited with the Freeman-Lemaitre-Robertson-Walker metric, which is a mathematical description of what happens in an expanding universe. Caveat for those who are pedantic, you need to assume that the universe has two properties. One is that it has to be isotropic. It has to be the same in all directions. From what we can see, that's a reasonable assumption. And then you also have to assume, to apply this, you have to assume that it's homogeneous. In other words, that you could swap bits of it over without it looking any different. And we think that that's true on a large scale. Obviously, it's not true on a local scale because where you sit is different from my bit of the universe. The Earth is different from the Sun. The solar system is different from somewhere out in the midst of space between the galaxies. But on a large enough scale, I think you could swap over large chunks of the universe without noticing any difference in its properties. So we can assume that the universe is homogeneous and isotropic. And then from this model, you can predict what's going to happen to the universe. So graphs like this get drawn. The scale factor on the axis is just how big the universe is. So as you go up, you get bigger. And then this is just time in some physical units. So you can see there are a couple of possibilities for the universe. One is that it just expands forever. One is that it expands forever, but it slows down. And another is that it expands and slows down and then reverses to something that tends to be called the Big Crunch, which is the opposite of a Big Bang. I've always liked there's an alternative name for it, which is the Knabignib, which is the opposite of a Big Bang, which I quite like. And initially, people were quite into this sort of Big Crunch measure. I should say the thing that matters is how much stuff there is in the universe. The more matter there is in the universe, the more important gravity is. And gravity can slow the universal expansion. And so this is a race between the expansion of the universe and gravity pulling it back together. So a universe where there's lots of stuff will collapse into a big crunch. And this is well understood. I really like this paper from Martin Rees, who went on to be astronomer or has been a Gresham professor of astronomy, one of my predecessors, from 1969. This is one of the first people to study the collapse of the universe seriously, and I really like his cheerfulness, in which he describes this as a catastrophic process whereby the contracting cosmos reverts to primeval chaos, which is indeed what would happen. So in this collapsing universe, this big crunch of a universe, we know that the reversal, even when Rees was writing in the 60s, we knew that this was at least something like 10 billion years into the future before this reverse would happen, based on what we knew about the universe. And what would happen is that you would start off not noticing anything at all, really. You still make your observations, but you'd slowly realize that instead of galaxies receding from you, you would see them heading back together. When the universe had contracted by a factor of 5, so quite a long way from its maximum size, clusters of galaxies would merge together. So you end up with just one big galaxy cluster. And then when there's another contraction by a factor of 10, so really quite advanced into the crunch, galaxies would merge together. So the stars, which may still be around at the time, would then just be a soup. So you just have stars moving around. And it turns out the mathematics is such that stars, even in this dense collapsing universe, probably wouldn't collide with each other very often. There's enough space between the stars that that wouldn't happen. But all the radiation in the universe, all the light both that left over from the primordial conditions after the Big Bang, but also light emitted by the stars. Because it's been in a universe that's contracting, that would begin to heat up. And so you begin to be bathed in a background of warm radiation. And eventually, you reach a point where that background radiation is about the same temperature as the stars, which means the stars can no longer lose energy by radiating away light. So you now have a nuclear furnace burning hydrogen into helium that can't get rid of any energy. And I couldn't find, as far as I could tell, no one in the literature has done a serious study of what such a star would be like, but I'm going to guess it's not good and that it's not stable. And eventually, such things would be ripped apart, and we end up with a collapsing cosmos that's full of particles and radiation. We, in fact, get the chaos that Martin refers to as we head towards the moment of the big crunch. Now, one of the reasons, I should probably say that physicists have tended to take this sort of Armageddon as a hopeful picture, particularly if you're a particular kind of cosmologist, because the idea of a big crunch gets you out of having to explain the Big Bang, which is the big problem. I've said in these lectures before that while we know that the universe, there's good evidence the universe was in a hot, dense state 13.8 billion years when it started expanding, we actually don't know much about what happened just before that point. We don't know much at all. We have very little idea. And so the Big Bang itself is a mystery. But if you have this expansion and contraction, then you just have an endless series of universes that expand and collapse, and then they rebound due to magic. You invent some sort. We don't understand the physics of the Big Bang, so it seems reasonable that a big crunch might rebound. Sure, I mean, it's in the bit of physics we don't understand, so fine, I'll allow that. So then you have it expands, and then it reaches a maximum amount, and it collapses back down, and you get this bouncing universe that extends forwards and backwards for eternity. And while our universe doesn't get to exist forever, the long chain of universes that it's part of does. That feels vaguely reassuring, and we've explained the Big Bang. You might even, perhaps if you are a particular kind of theorist, spend your time trying to work out whether information can be copied from one universe to the next, so that perhaps we could somehow send a message or transmit ourselves or whatever fanciful science fiction you would like into the next universe and thus exist forever. But there's a problem with this, and the problem is one that dogs physicists throughout. It's the problem of entropy. And entropy is something we live with and experience every day. Here is a simple demonstration of entropy. This is a dog looking at an egg. If you watch the egg carefully, you can see that on contact with the ground, it experiences rapid disassembly. You're familiar with this physics, yes? The point is that if I play that video again, and then reverse it, only one of those things makes sense in our world, right? Eggs don't spontaneously reassemble and jump up into somebody's hand. The universe tends to disorder. Things move from an ordered state to a disordered one. This is the second law of thermodynamics. This is the law that was memorably summarized by Flanders and Swan. Heat can't flow from a colder to a hotter. You can try it if you want, but you'd far better notter, which is a useful aide-memoire. The point is that order tends to disorder. The reason the dog, this is my dog, Mr. Max, by the way, the reason he's there is that I wanted to remember to point out that he is essentially a machine for creating disorder out of order. That's true both in terms of distributing things around the house, but he takes in quite ordered kibble and emits heat and energy. So life itself obeys this rule. Even though we seem to be complex ordered creatures, we are, by existing, creating disorder. And so in our bouncing universe, the problem is that that final state, the chaos that Martin wrote about, the point where you have a hot universe full of atoms and radiation and energy, that's highly disordered. It's a high entropy state. And so when my universe rebounds, assuming that my magic physics obeys the second law of thermodynamics, then I end up with a new universe that's already high in entropy. So nothing can happen in it. We get stuck in a rebound that produces a universe in which galaxies can't form, stars can't form, life can't form. And we're left with the mystery that our Big Bang produced a low entropy state, which is a fundamental and deep mystery. So this rebound doesn't really get you out of explaining anything. But the more important question is probably whether we really do live in a universe that's going to collapse and whether these theoretical arguments are going to be important. And so what we want to do is measure the amount of stuff in the universe, come up with a way either to measure the mass of all the galaxies and matter in the universe directly, or to measure directly how fast it's expanding and how that's changing over time. So we either measure the mass, we can infer how much gravity there is and then say whether the universe will slow down or not, or we can look directly over time and see whether it's slowing down. And this was the big project for observational cosmology for the second half of the 20th century. New and marvelous telescopes were built to do this. I really like this photo. This is the 200-inch Palomar telescope. This is its mirror being transported across the US by train. People came out in towns across the United States to applaud the telescope mirror as it headed to Palomar. Would that they would do so still. And this thing was built. This was the largest telescope in the world for about 30 years. And it was built to try and find ways of weighing the universe. What astronomers wanted to do was to find things in the local universe that they could see also in the higher redshift, the early universe. So for example, there was the idea that the biggest galaxy in a cluster would always have the same mass, based on the physics of clusters. Then wherever you saw a galaxy cluster, you'd know how much mass was in the biggest galaxy, you'd know how bright it was. So like with Henrietta's Cepheid variable stars, you'd know the distance. And this project basically failed because the universe changes and evolves over time. And so it wasn't till the 1990s when we started to get detailed observations of the cosmic microwave background, which here I'll just say is the light left over from the Big Bang, from the time in the first 400,000 years of the universe's existence where it was hot enough that light bounced around. If you want to know more about the cosmic microwave background, you can go back to year one and listen to an excellent lecture on it. But what astronomers were able to do was, this is a map of the whole sky with that ancient light. And you can see here that there are small variations. There are places where the light is a slightly different color, which represent density fluctuations, places where there's slightly more matter or slightly less matter. And from this pattern, it's possible to constrain the cosmological parameters. And what they showed was that we lived not in a universe that was going to collapse into a big crunch, but in what's called an open universe, one that's going to expand forever. And so the story of the future of the universe becomes very different. We can start by thinking about the stars. This is the Hertzsprung-Russell diagram. This shows all the many different types of stars split by color and brightness. So the sun is more or less in the middle of this diagram. But you can see there's this main sequence of running from top left to bottom right, this fundamental pattern. And it's there as a reminder that what happens to a star depends on its luminosity, which depends on its mass. So the biggest, brightest stars run through their fuel very quickly. The most massive stars in the universe probably exist as rock stars, living fast, dying young. They exist for only a few tens or hundreds of millions of years. And when they reach the end of their lives, they will explode in bright supernovae and produce black holes. A little later on, we've already talked about sun-like stars. Actually, before you get sun-like stars, stars a few times the mass of the sun will follow a similar process. They'll last a bit longer, hundreds of millions to maybe a few billion years. They will explode. They produce neutron stars, which we see as pulsars, for example. And then small stars like the sun, once they go through that red giant stage that I started off talking about, they produce white dwarfs. This is Sirius, and the small dot in the bottom left of it, that's its companion white dwarf. And so, as I break the news to you that the universe is already past its best in the sense that more stars die each year than are being born, will slowly replace our brightly lit sky full of stars with these dense remnants, with white dwarfs, neutron stars, and black holes. And at some point, in something like a billion years' time or so, the last star will be born. And if it's a small star, billions of years later, maybe as many as something like 100 billion years later, it will fade out and produce a white dwarf. And so we're left with a universe that has light, leftover starlight, leftover cosmic microwave background, and these dense remnants, expanding still. After that, we rely on particle physics to keep us going. We think, many current theories of particle physics suggest that the subatomic particles from which these things are made, things like protons, are unstable. And protons themselves will decay either in a few billion years, or depending if which particle physicists are right, in a billion years. But between those two, they will decay. And what that means is the white dwarfs, which are supported by subatomic particles, will wink out. They'll fade first, but then they'll disappear. Neutron stars go too. And Stephen Hawking taught us that black holes, if he's right, black holes evaporate slowly through a process called Hawking radiation. And so in the far future, we're left with a universe basically just filled with light that's expanding forever. And so that light gets dimmer because it gets spread out and it gets redshifted, so it becomes redder. So the universe is full of light fading gently to black. And actually, we know something about what that will be like. And we know that because of two teams of astronomers who in the 1990s realized that they could study objects like this one. This is supernova 2014J, which was discovered just up the road in Mill Hill Observatory by Steve Fossey and a couple of students while they were waiting for pizza. It's a whole other story. This is an important nearby supernova because it was what's called a Type 1a supernova. And Type 1as always go bang with the same brightness, same luminosity. Or actually, you can look at how they change over time and calculate the luminosity. And if you know their luminosity, then like Henrietta's Cepheids, you can measure their distance. And so these things, which can be seen across a large fraction of the universe, can be used to measure the distance to even quite distant galaxies. And so we can play this game of calculating how the expansion of the universe has changed over time. And when these projects, one run by Saul Perlmutter and Adam Rees in the States, and another by Brian Schmidt in Australia, when these projects were set up, what they thought they were doing was measuring how fast the universe was slowing down, trying to work out how much stuff there is, and therefore how the universal expansion is slowing down, to get a different handle on this than you can get from the cosmic microwave background. But what both of them found in papers published within a few weeks of each other back in 1997 was that the expansion is speeding up. So we live not in a big crunch universe in orange here, not in an ever-expanding universe like the blue or green lines, but in a universe that sometime in the last few billion years seems to have started accelerating in its expansion. This was a nearly entirely unanticipated result. And we still don't understand the nature of this force that must be causing this expansion. We call it dark energy, just to give it a name. It's a terrible name, because I don't know what it means for energy to be dark, but nonetheless, that's what we call it. And we live in this accelerating universe so that the expansion will not only continue forever, but it will get faster and faster. And so the obvious question is whether the acceleration will accelerate, whether this is a process that would lead to what many cosmologists have called the Big Rip scenario. And the Big Rip is really bad news, because in this scenario, we don't have our nice long period of light, and before that, black holes, neutron stars, and white dwarfs. What we have is a force that will rip even atoms apart. I am told, by the way, that it will be mercifully brief. The period in which you exist before your atoms are pulled apart will be very rapid. And we are talking about something that might happen in billions of years' time. But lots of effort is being put into determining whether the strength of this dark energy, this accelerating force, is changing with time. Partly because we'd like to understand whether we live in this big rip scenario, but also because the hope is that if we can find some way in which it's varying, we might have a clue as to what on earth it is. We are still stymied by lack of evidence. Other than that we know it exists, we have very little to go on in trying to understand this mysterious dark energy. And there's a project called DESI, which uses this telescope on Kitt Peak in Arizona to map the nearby galaxies that you can see in colors here, compare those to what we see in the microwave background. And they published results a few months ago that, taken on their own, seem to suggest there is a slight change in the strength of this dark energy. If true, it's a hugely important result. It's less clear that it's right when you combine it with all the other ways we have of measuring this, but more work is needed. So it's possible that we live just on the other side of this line that leads to a big rip, but it's possible that we live just on the side of the line that leads to an accelerating universe that slows down its acceleration. But in either way, we end up in this bleak future with an expansion forever into just a sea of radiation. But things go weird at that point because physicists like to imagine bizarre scenarios. And so far, and I'm going to steal from the wonderful online comment XKCD, we've talked about, we leave the 5-day forecasts to meteorologists, 5-month forecasts anyone could do, 5-year forecasts I guess are fine, 5 million year forecasts we've talked about, the 5 billion year forecast is bad with the sun, and then we've got the 5 trillion year forecast which is well understood. But the question is, does anything happen after that? Once you have this expanding universe that's nothing but radiation, what happens next? And some people would like to argue that actually, out of this fairly bleak future, there's hope in that if you've got an infinity to play with, anything that can happen will happen. So even staggeringly unlikely things will happen. And the way this is often framed in the last line of this cartoon is usually the concept of something called a Boltzmann brain. And the idea here is that if you have an ever-expanding universe full of radiation, and you have a process either because particles and radiation are moving randomly or because of some quantum effect in which you can spontaneously produce a structure, then you should expect everything to briefly appear randomly in the universe. So my IKEA bookcase will appear. It's staggeringly unlikely that it will do so, but at some point, because you've got infinity to play with, that will happen. In fact, if you believe that our brains are just an arrangement of atoms, if you accept that for now, then you should expect at some point a brain to appear with all of your memories and thoughts right now should appear suddenly in the distant universe, briefly, before scattering back into quantum fluctuations or an arrangement of particles. This idea is usually known as a Boltzmann brain, and it creates some quite disturbing scenarios. For example, if you can do the calculation as to how often this will happen in an infinitely expanding universe based on the cosmical parameters, and what you conclude is that it's overwhelmingly likely that at any given moment when you're having a thought, you're more likely to be a Boltzmann brain that's just popped into existence in the far future than you are to be a person living on Earth right now. And in almost all of those cases, you will almost certainly disappear almost instantly because you'd return back as a fluctuation into the quantum mess that exists in the far universe. Now, often in my position, when people start talking about these Boltzmann brains, they're one of those things that I think can come across as sounding like a deep and profound truth. I can imagine lots of you in the pub later telling your friends that this mad lecturer told you that you were probably just a floating brain in the far future, and that to be a proper student of science, you have to accept that notion. But you have to realize this is a thought experiment that we don't like. The great Sean Carroll, who's written about some of these profound things, said, look, we're not arguing that Boltzmann brains exist, we're trying to avoid them. If our theory says that you should be a floating brain in the far future, then there's something wrong with our theory. We'd like to get rid of it and perhaps have a universe where nothing happens at all. This is the kind of thing I mean when I say that thinking about the far future, thinking about the physics that might exist in this very unusual state of a bath of radiation at very low temperature, that's as different from what we do know now as the Big Bang is, where we have a bath of radiation at very high temperature just after the Big Bang. And so I think we've got more work to do. But I promised you hope, and so let me try to give you a scenario to cling on to. I am a big fan of a hypothesis that actually goes back a long way about what might happen in this far future. So I said that anything that's possible will eventually happen in the far infinite future of the expanding universe in which we seem to live. And if you'll allow me one piece of magic physics, let's assume that our universe can produce further universes, that there's some process that means a universe can bud off from an existing universe, that can be conjured out of the vacuum. Indeed, you can assume that our universe started in just such a way. Then in the far future, this process, if it's possible, will happen again and again and again and again. And what's nice about this thought that other people have had, Lee Smolin and others have popularized, is that maybe those new universes will inherit some of the properties of their parent universe. Maybe you have some natural selection in there as well, some variation. But what that will mean is that you can use this as an explanation for why we live in a long-lived universe. Because only long-lived universes will give birth to new long-lived universes. If your universe was doomed because it had too much matter to collapse in a big crunch just a few million or billion years after it started, then it would produce no daughter universes. And so for the price of inventing a completely fictional process by which new universes can be budded, I can explain why our universe has the ending that it does. And I think that's actually rather beautiful. I have no evidence that it's true, but it's a nice idea. And I think I started by saying that when astronomers think about these things, they tend to do so in a sort of jovial and bleak fashion. And I've joked throughout that this is a depressing view of the universe. But I actually don't think it is. I think there's two things to say. One is that we are the bit of the universe that thinks about it. And we're able to imagine a process which in the far future might create more universes with more beings to think about it in. I find that uplifting. I have to say, on a random Monday, it's actually quite relieving to know that everything in the end will disappear into a sea of radiation. It certainly helps me deal with my inbox. But I will try and leave you uplifted. And to do that, I'd like to welcome to the stage a good friend of mine. Please welcome Steve Pretty. So Steve is a very accomplished jazz musician, is the leader of the Hackney Colliery Band, amongst much else. He's also one of the premier player of conch shells, which we'll talk about some other time. But he and I met and shared a love of music and astronomy, and we've ended up building a show called The Universe of Music. And one of the things we do in that is talk about the end of the universe. And so we thought we'd finish with that this evening. Some of the words in this are from an amazing book called Last and First Men by a philosopher in Oxford writing in the 1930s called Olaf Stapledon. And Last and First Men is this breathtakingly ambitious science fiction novel which sets out to be a history of something like the next 200 billion years. I give you all permission, you all have to read it, but I give you all permission to miss the first 100 pages. So the first 100 pages are a Marxist analysis of 1950s politics on Earth. But everyone kills themselves at the end of that. There's a nuclear holocaust, and then the real stuff happens. And Stapledon is a writer beloved, I think, of astronomers and cosmologists, because he writes beautifully about some of these big ideas. So from me and from Steve Pretty, we'll give you the end of the universe. past its best. Stars die and are not replaced by new stars being born. The galaxies we see around us are fading away, slowly, star by star, as each dies either as a supernova or fading to a white dwarf. Soon, the last star will shine its last light and will be left with a universe filled with compact remnants, white dwarfs fading to black, black holes, and the occasional neutron star. The amount of the universe we can see is dropping. Dark energy sees to that. And so each of these stellar remnants will become increasingly isolated. And eventually, as proton decay comes from them all, white dwarfs will disappear, black holes evaporate, neutron stars fade into nothing but a sea of radiation, expanding outwards, propelled by remorseless and endless dark energy into a sea of radiation that will last for infinity, with nothing ever happening. But in the beginning, there was great potency and little form, and thenceforth there's been a long and fluctuating adventure towards harmonious complexity of form and towards the awakening of the spirit into unity, knowledge, delight, and self-expression. Nowhere, and at no time as far as we can tell, at least in this galaxy, has this adventure reached further than it has in ourselves. And in us, what's been achieved is but a minute beginning, but it is a real beginning. Humankind in our day has gained some depth of insight, some breadth of knowledge, some power of creation, some faculty of worship. We've looked far afield, and we've probed, not altogether superficially, into the nature of existence, and have found it very beautiful, and also terrifying. We propose to ourselves a very long and arduous future, which will culminate, at some time before the end, in the complete achievement of the Spirit's ideal. Thank you very much. Steve Pretty.